superposition theorem. The statement says, in a network of linear resistances containing more than one generator, that is more than one EMFs, the current which flows at any point is the sum of all the currents which would flow at that point if each generator were considered separately and all other generators replaced for the time being by resistances equal to their internal resistance. Note, other generators, if they are ideal voltage sources, then they are represented with short circuit, and if ideal current sources, then it is represented with an open circuit. This should be kept in mind. According to superposition theorem, if there are more than one EMF acting on a linear bilateral network as shown in this diagram, the EMF will act independently as if the other EMF is not there in the circuit. That is, the other EMF is replaced with a internal resistance. If it is an ideal source, then it is replaced with a short circuit. If it is an ideal current source, then it is replaced with an open circuit. And as per this diagram, E2 is replaced with an internal resistance as shown. And the next diagram, E2 is acting on this network and E1 is replaced with its internal resistance, and the currents are calculated. The currents which flow in the network is the algebraic sum of the currents which would flow when the independent voltage source is acting on the network, leaving other with internal resistance. Here in this diagram, I1 is the current calculated with E1 as the voltage source and E2 taken as the internal resistance, that is I1 dash. And next, E2 acting on this network with E1 taken as internal resistance and I1 double dash is calculated. The net result I1 is the algebraic sum of I1 dash minus I1 double dash. This how I2 and I are calculated. We will look at the example. Now consider this example network where I have shown the values now. The EMF 1 or E1 is shown as 6 volts with an internal resistance of 0.5 ohms, and E2 is shown as 12 volts with an internal resistance of 1 ohm, and the resistors 2.5 ohm, 2 ohm and 6 ohm are shown as per this network. Now we need to find the currents I1, I2 and I. As per the superposition theorem, this network is now replaced with 1 ohm resistor, which is internal resistor of the 12 volts EMF, and the 6 volts EMF is alone acting on this network. Now at point A and B there are two paths, that is 6 ohms resistor is in parallel with 2 plus 1 ohm resistor, thereby the equivalent resistance at point AB will be 2 ohms. Now the total resistance of the network is 0.5 ohms internal resistance of EMF plus 2.5 ohms plus the equivalent resistance 2 ohms, that is 5 ohms is the total resistance of this network. Now I1 dash is the current which flows from 6 volts EMF to the network. I1 dash equal to 6 volts by the total resistance of the network, that is 1.2 amperes. So I1 dash would be 1.2 ampere. Now at point A, this I1 dash, which is 1.2 ampere, will be splitted into two branches. So the current I dash flowing through 6 ohms resistor will be I dash equal to I1 dash, that is the total current, multiplied by the opposite resistance, that is 2 plus 1, by the total resistance, that is 6 ohms, 2 ohms and 1 ohm, that is equal to 1.2 into 3 by 9, that is 0.4 amperes. So we know I dash is now 0.4 amperes. Now similarly we can find I2 dash, which is flowing I2 dash equal to the I1 dash into opposite resistance, that is 6 ohms by sum of the resistors 6 plus 2 plus 1, that is equal to 1.2 into 6 by 9, that is 0.8 amperes. So I2 dash will be 0.8 amperes, or simply the difference of the current, that is I1 dash minus I dash will be the current flowing through this branch. Therefore I2 dash equal to I1 dash minus I dash, that is 1.2 minus 0.4, that is 0.8 amperes. And here note that the direction of currents, because the 6 volt EMF is acting on this network, so the current would be leaving from the EMF source into the network, thereby the arrow shown for I1 dash is towards right, and the current will be split into two branches, I1 dash which would flow from point A to point B, and I2 dash will be flowing from point A into the network. This is the current direction for this network when a 6 volt battery is acting. Also now we will look at when 12 volt battery acts on this network. Now considering only 12 volt battery acting on this network, and the internal resistance of this 6 volt EMF is replaced as 0.5 ohms, we will calculate the currents flowing in this network. Now the directions of current is as shown, as 12 volt source is only acting on this network. Now this 12 volt battery feeds the current I2 double dash into node A, and at node A this current is split into two branches, that is I1 double dash and I1 I dash. Now we will find out the R equivalent for these parallel resistors. 0.5 and 2.5 are in series, and the combination is in parallel with 6 ohms resistors, thereby the equivalent resistance at point AB is 2 ohms. The total resistance is 1 ohm, the internal battery resistance, plus 2 ohms plus the equivalent resistance at point AB, which is 2 ohms, that is equal to 5 ohms. So total resistance of this network is 5 ohms. Now I2 double dash is the current flowing into the network. To calculate this, 12 volt EMF source divided by the total current, total resistance, which is 5 ohms, is 2.4 amperes. Therefore, I2 equal to 2.4 amperes. At point A, this current is split into two branches, which is I1 double dash and I dash. So to find out I double dash, 2.4 ampere current multiplied by the opposite resistance 2.5 plus 0.5, which is 3 ohms, divided by the sum of the resistances, which is 9 ohms. So 2.4 into 3 by 9 equal to 0.8 amperes. 0.8 ampere is a current which is I double dash. To find out the current I1 double dash, 2.4 amperes into the opposite resistance 6 ohms by the sum of resistances, that is 2.4 into 6 by 9 equals to 1.6 amperes. 1.6 amperes is the I1 double dash current, or in other way, I1 double dash equal to I2 double dash minus I, that is 2.4 minus 0.8 is 1.6 amperes. This is how we have calculated the currents when a 12 volt battery is alone acting on this network. Now, as per superposition theorem, the superimposing of these currents will be the resultant currents on the network here. Let us see that. Now we have calculated the currents in the network considering the EMFs separately. Now, as per the superposition theorem, when two sources are acting on a network, the current would be the algebraic sum of the currents when each source is acting independently. Now, I1 current is equal to, I1 current is shown as per this arrow when 6 volts source is acting on this network. So I1 is considered as positive, minus, because the I1 direction is opposite to that of the current when 12 volts EMF is acting, minus I1 double dash, that is 1.2 ampere minus 1.6 ampere, that is minus 0.48 amperes is the current which is flowing as I1. Now let us find I2 current. I2 current, when 12 volt EMF is acting, it is as shown in the arrow. So I2 double dash, and I2 dash is opposite to that of the current direction shown here. So I2 double dash minus I2 dash, that is 2.4 ampere minus 0.8 ampere is 1.6 amperes. So I2 is 1.6 amperes. Now the current I dash plus I double dash equal to 0.4 plus 0.8, that is 1.2 amperes is the current I. So this is how we will evaluate the currents or voltages using superposition theorem. If you want to know the voltage drop across 6 ohms resistance, it is simple now. As we know, the current I is 1.2 amperes. The voltage drop across 6 ohm resistor, that is V 6 ohms. Let us say it is 1.2 ampere into 6 volts. So similarly, we can calculate the voltage drops across all the resistors you have. This is what is superposition theorem.